Let's go and talk about the daily problem. Again, last class, we started, yes? Yes. Yeah, okay, question about big O notation, yes.
I'm wondering if it's sufficient to say that if you know that one function dominates another, if that's, like, is that okay to say as a reason of why one function's big O of another, or do you have to give the example with finding C and that?
Okay, so it depends upon, you're asking about, if I give you a problem on the midterm about proving something is big O of something. You know, if I'm asking you to say, is this function big O of that function, and I say show your work or something like that, you should be giving me the constants to prove it, right? If I'm asking you to show, does this dominate that, you probably want to do the limits, if I'm asking you to show this, okay? If on a true-false question, do I say, is this big O of that, okay? There's no place for you to write in your little work, okay? And so in that case, you're off the hook. Yeah, but you should be, you meant...
Are the limits enough to say, you know, if the limit tends to 0 of like 1 over the other as x approaches infinity, is that enough to say, therefore, one is big over the other?
I say one function dominates the other. Yes, that would be enough to prove a dominance, as we talked about. Okay. Okay, let's move on to what I want to cover. If we have time at the end, maybe we'll do some review. But okay, any questions? Okay, so I wanted to talk first of all about the problem of the day, which is this one on nuts and bolts, sorting nuts and bolts. Last class, okay, so we talked about sorting, we talked about merge sort, we talked about quick sort. The nuts and bolts problem is as follows. I give you n bolts. Does everybody know what a bolt is? A bolt is this thing, that piece of hardware that looks sort of like this, and it's got a screw thread on it, right? That is a bolt. What is a nut? A nut is one of these hexagonal things, okay, that has a screw thread in here, and nuts screw into bolts, and you build things from them, right? We're assuming that we've got a world where we have n bolts, each of which has a different width, and n nuts, each of which has a different hole width, okay? And our goal is to pair the nut with the corresponding bolt, okay? You can imagine you've got a pile of nuts, you've got a pile of bolts. For every nut, there is a bolt that fits it. Now, the trouble with this is that because the differences, anyone who's ever worked with nuts and bolts, you can't tell by inspection whether a nut will screw into a bolt, right? You could very well have a situation where you try to put the nut on the bolt and it doesn't fit on. In that case, the nut is too small for the bolt. Does everybody see that? You could have a situation where the nut doesn't screw over the bolt, right? It just goes like this. In this case, the nut is too big for the bolt, right? Alternately, they will screw and fit tightly. Does everybody see that? That's what we want. Now, because these precisions are so tight, you can't take a look at two nuts and tell me which is bigger. And you can't look at two bolts and tell me what is bigger. The only comparisons you can do are a nut against a bolt. Does everybody understand the problem? So my goal here is to try to match nuts to bolts. So I've got n nuts, n bolts. Can anybody give me an order n squared algorithm to pair up the nuts with the bolts? Let's try this, okay? You. What? Bubble sort. Okay, so bubble sort, I don't know quite what that means for the following reason. In a bubble sort, I've got n items, and I'm comparing each item against each, you know, I can compare any of my items against any one of my other items, okay? In this case, I've got nuts and bolts. I can't compare nuts against nuts or bolts against bolts. I can only compare nuts against bolts. Okay, what do you think? Okay, does everybody see that? So what he's suggesting is basically doing all pairwise comparisons. Okay, here I have a pile of nuts. Here I've got my pile of bolts. Okay, I'm going to pull out a bolt, compare it against all n of the nuts, right? One of them is going to work. Once that's done, I'm going to take my pair and toss it aside. And now I'm going to pick up another bolt and compare it against another nut. Does everybody see that? In the worst case, I'm going to get very unlucky with each. I pull out a bolt, and it's always the last nut that I get. Does everybody see that? That's going to be n squared comparisons in the worst case. Any questions? That's good. Now let's try the second problem. It's kind of a warm-up here a little bit. What if I want to find, instead of matching up all the nuts and the bolts, I only want to find the smallest bolt and its corresponding nut? Show that I can do this in, it looks like 2n-ish comparisons. Yes, you.
Pick a nut and a bolt, and then throw out the bigger of the two, and then keep comparing and throw out the bigger.
Okay, so right, so what he's suggesting is the following. That I'm going to pull out a nut, and I'm going to pull out a bolt. Does everybody see that? Okay, and one of them is going to be bigger. If it is like this, it is the, which is bigger, the bolt is bigger, right? That means the nut is smaller. If it goes like this, the bolt is smaller. The claim would be that I pull out these two, either they are the same, or that one is bigger than the other. If one is bigger than the other, I toss that away. Does everybody see that? And how many times can I toss a nut or a bolt away before this stops? Okay, there's 2n minus 2 things that will get thrown out, right? Because at the end, I'm ending up with one nut and one bolt, right? So this is interesting just as a way of counting. Does everybody see that there's a total of 2 to n minus 2 things that have to happen? In each comparison, assuming that they are different, I end up tossing one away. What if they're the same? What do I do if it's the same? Yeah? Put one of them to the side. Don't throw it out, right? But maybe paint them both red. Keep them to the side. Keep it in mind. And now compare, if I kept the nut, pull out a bolt, okay? If the new bolt I pulled out was smaller, then both my nut and my bolt that I matched were no good, right? And I throw both of those pieces away, right? So basically, at any point, I'm only going to have at most one nut and bolt combination that's potentially live. Usually, it'll be only one of them, okay? Until to the end, I'm going to have this what I want. Any questions? Yes.
So what two comparisons here are we not throwing out?
What you're not throwing out are what you end up with at the end. Remember, how many nuts and bolts are there total? How many are there not thrown out at the end? 2. So the 2n minus 2 is the number of throw-out steps, right? And it should be that in general, it should be clear that assuming that if we didn't have this problem with equality, we would always toss out one every step. We've probably got to be a little bit careful to make sure it's not 2n minus 3 or 2 or plus 1 or something like that for the special cases of that. But it should be clear that it's 2n minus 2-ish, okay, for this. And we can try to be more precise about it later. Okay? Any questions about that? Yes?
So this still means then 2n give us most of the points, so the minus 2 would just be like 1 point or something?
So something like as a strategy here, if I was going to demand this 2n, if I said 2n plus 2 is the right answer, and you gave me an argument like that, maybe I'd say, oh, you didn't handle the boundary case here. But you're right, that's the big picture you've got. Okay, yes?
What does minus 2 represent?
Minus 2 represents the, let's say we have 4 things. Okay, at the end we want, what is it at the end? We wish to find the smallest nut and its corresponding bolt. Means we want to throw out anything that is not the smallest nut and its corresponding bolt. We started out with a pile of n nuts and a pile of n bolts. If we're ending up with 1 nut and 1 bolt, how many things are we throwing away? Anything that is not the smallest nut and the smallest bolt, which means n minus 1 nuts and n minus 1 bolts, which is 2n minus 2. Any questions? Okay, those are warm-ups for what is really the interesting one. Now, I want you to match up all the nuts and the bolts in n log n time. Notice we could use the part 2 to do selection sort, okay, by pulling out the smallest nut and bolt, and then repeat, but that's going to be an n squared algorithm. Okay, yes, what do you say?
So since you can only compare nuts and bolts, you would take, say, a random nut, and then you use that to partition the bolts. And then eventually, since there's only one matching one, the matching bolt will be used to partition the nuts. And then afterwards, you have like two, or maybe not two equal halves, but you're partitioning both the nuts and bolts into two, and then you recursively go.
Okay, so you are thinking which sorting algorithm is inspiring you? Quick sort. Okay, she wants to quick sort these nuts and bolts. What is she going to do? She is going to pull out a random nut. Okay, here is a nut from the pile. And she is now going to compare it to every one of the bolts, right? And some bolts are going to be small bolts. Some bolts are going to be big bolts. And one bolt's going to be just right. Does everybody agree with that? Okay. How much time did it take to do this partitioning against that nut? How many time did it take to compare all the bolts against the nut? N, right? And this should smell just like a quicksort partition. Does everybody see that? And now she's not done yet. She is going to take this bolt and do the same thing to the nuts. And for every one of the remaining nuts, she already knows this is just right. There's n minus 1 nuts left. She can tell which ones are tiny little nuts and which ones are big nuts. Okay? Any questions about that? And once that is done, to finish the quicksort thing, she is going to sort these independently of sorting those. Does everybody see that? All the smaller nuts and bolts are now in these two piles, and all the bigger nuts and bolts are in these two piles. And this is two independent sorting problems, the size of which was basically picked uniformly from 1 to n. Half the time she would have picked a good nut, by my notion of a nut in the middle from my quicksort analysis last time. Half the time she would have picked a bad nut. This is exactly the same as quicksort. Okay? And so the expected analysis of this should be n log n. Any questions?
Could this be maybe improved slightly by, instead of, like, so if you sort the bolts first, partition the bolts, could you just then pick another random nut and figure out which partition it should be the pivot of, as opposed to also partitioning the nuts completely?
Okay, not sure I understood what you were saying.
So I'm saying instead of, let's say we're sorting the bolts first, right?
Yeah. Well, you say you're sorting the bolts first. You can't sort the bolts first. This is the whole point of these things.
Pivot the bolts first.
You're going to partition.
Yeah.
Okay, so we partition the bolts first. Okay, yeah?
Then can I, instead of also partitioning the nuts in the same way with the matching bolt, can I just pick a random nut, figure out which partition it could be the pivot of, and then use that so that we don't have...
Okay, so what I think what you're trying to say is the following. Suppose, let's say, we start pivoting, we pick our random nut and the bolt, a random nut, and when we toss this thing into the, we use it to partition, we find that we had a lopsided partition. Maybe what you're saying is what I really want my pivot to be is one of these guys. Maybe I could shift into that. Is that what you're saying?
No, I'm just saying, so if we partition the bolts, instead of also partitioning the nuts in the same way,
Okay.
then just select a random nut and then use like binary search to figure out which partition it can be the pivot of.
Okay, so you're saying that instead of partitioning it, pick a different nut and do it half and half. Maybe kind of. What's clear is you don't get the same analogy with quicksort. That is the first observation here. The reason this is quicksort is that we have completely divided it into two smaller instances of the same problem, which are nuts and bolts that are paired up, that are, corresponding. Okay? So it is important that we do the second partitioning to create the smaller problem. Okay? Any questions? Now, what's interesting about this n log n algorithm? Can anybody suggest a worst case n log n algorithm for this? Merge sort. Now, what does merge sort mean? It means that if I've sorted half the nuts and bolts, well, I don't know quite what that means in this context. Okay? The interesting thing is, this is one where there does not seem to be an easy n log n algorithm for this in the worst case. There are some hideously complicated algorithms using high-powered algorithm tools for this. But this is an interesting example of why randomization can be a very, very good thing. This is an easy algorithm. This is an algorithm I expect everybody to understand in here. Okay? But if you asked for an n log n algorithm to do this, and I demanded a worst-case one, here is one where there really isn't a good, easy, worst-case n log n algorithm known for this. Okay? What makes randomization such a powerful thing is it often suggests simple algorithms that should perform that almost certainly will perform very well. Okay? In this particular case, you could get very unlucky always picking the smallest bolt, but frankly, you're not going to get that unlucky. If you always get that unlucky, I don't want to stand next to you in a rainstorm. Right? Okay? The truth is that if you're picking these things at random, half the time you're going to end up with a useful one, half the time maybe you won't, but that's enough to guarantee you n log n. Any questions? So with high probability, you will get an n log n time from this algorithm. Any questions about nuts and bolts or quicksort in general? Yes? You can't use quicksort for something that says worst case. If I'm demanding worst case, I say I want a worst case n log n algorithm. If you say, start by quicksorting these items, you're saying take off points. Okay? What should you say instead? Heap sort these items. It doesn't change anything, right? But that's basically, again, in principle, quicksort can be very bad in the worst case. Okay? Again, the worst case is something that you guys have probably seen in quicksort. If your pivot was always the last element in the array, if the array was sorted to start with, where would the last element in the array go as a pivot? If the items were sorted, it would go to the rightmost spot, right? So it doesn't do any division. If you now repeat on the remaining array, that's still sorted, right? So if you get unlucky picking pivots, it will take order n squared. Okay? But if you pick your pivots at random, it's extremely rare you should get that unlucky. Okay? Any questions? And that's the glorious thing about randomized algorithms. Any questions? Okay, so I'd like to talk a little bit about randomized algorithms and just make sure we understand that because it's an important idea. And then go into some other kind of approaches to sorting and things like this. But again, the normal way you would write quicksort, typically you pick your pivot element as being the element at the rightmost. That's usually how I would write it. Or maybe you say pick the median of 3 items, or how do you pick your pivot element? Okay? The interesting question is, no matter how you pick your pivot element, okay, if you pick your pivot element in a deterministic way, like the median of 3, somebody could design a worst-case data instance to give you. Okay? This is kind of, I guess, what I want to show you what's kind of cool about randomization, is that in some sense, in a randomized algorithm, there is no worst case. No worst case input, actually. That's the precise that I want to kind of show you. In quicksort, if you always pick the rightmost pivot, as I said, if someone gave you the items in sorted order, quicksort would take n squared. How many people believe that? Okay, any questions about that? That's kind of important to see. How many people don't see why, if I always pick the rightmost element as pivot, if the elements came in sorted order, I would be in trouble? Yeah? You don't see it? Okay, so let's take a look at this. Suppose I try to quicksort the items 1, 7, 14, 21, 34, 42, this thing. And I pick as my pivot this guy. And I'm now going to diligently partition all the elements into those that are smaller than me versus those that are bigger than me. None of them are bigger than me. All of them are smaller than me. Does everybody see that? So I put this guy's now in the right place. I've spent n comparisons. Smaller, 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 smaller. And now I'm going to recur on this piece. And now I pick this guy as my pivot. And everybody is smaller, 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 smaller. Does everybody see that? In each partition, I spend n work, and I've done nothing. Does everybody see that? Now, suppose does not mean picking the rightmost pivot is a bad idea, okay? No matter how you pick your pivot, if you pick it deterministically, there is a worst case input for it. Yeah?
But since they're already sorted, aren't you done after the first?
Am I done after the first round? The answer is no. All I know is that all these guys are less than me. I didn't compare these guys among themselves, right?
Okay.
All I know is those guys are less than me. Okay? So I still have work to do. Or at least I might still have work to do, and I got to do it, right? Does everybody see that on this particular example, if I pick my pivot as being the rightmost element, this will be n squared, right? Now, I could do, what if I always picked the pivot as being the first element? Would have been just as bad, right? Now, some of you say, well, what if I take the median of my first one, my last one, my middle one, and my last one? That's something you may have learned, right? Median of 3, right? Recognize that if I wanted to construct a bad example, I could make it so that was the biggest, second biggest, and third biggest item in the array, right? And now your partition is almost near the very end of the array. And if I do that recursively, that construction, I can construct a worst case example for any quicksort you give me where you have a fixed rule for constructing the pivot. Any questions? Yes?
What if you use the median medians to find the pivot?
What if I use the what?
The median of medians to find the pivot.
The median of medians. Okay, if I had went through and analyzed all of these n elements and found the median, that would make a perfect pivot, right? Now, to find the median, I've got to look at every single, at the least, look at every single element once, right? And so it's expensive to try to find the median. But if I do any kind of constant time rule to try to select the median, I'm in trouble, right? Does everybody see that? Potentially in trouble. If my enemy was designing the example, I would be in trouble, right? If in the presidential campaign, okay, Hillary Clinton announced that to make government more efficient, she was going to mandate the use of a very good quicksort. What would Trump say? You're using the last element in your median? Try sorting this example, huh? Okay, your example looks bad, right? Your quicksort is slow, you're wasting government money, right? You're not fit to be president, okay? Yes. Okay, could Trump figure that out? Okay, he's got the best people working on it. Is my okay. What is interesting now, if I pick the... Okay, so any way I pick the pivot deterministically, there is a worst case example to be given to me. Right? Because everybody should believe that. Okay, unless I analyze really hard and find the median. Okay, and that's going to be very expensive. But suppose instead I pick as my pivot a random position in here. Okay? I'm going to flip a coin or pick a random number from 1 to n and let that be the index of my pivot. Okay? Now, Trump can't, the guy can't give me a bad example. Why is that? No matter what example they give me, if I'm picking the pivot at random, no matter where they carefully planted the one that's going to screw me, I'm going to have a 1 in n chance of picking it, and an n minus 1 chance out of n minus 1 over n chance of not picking it. Does everybody see that? So if there is a poison pivot here, the odds of me picking it was 1 out of n, regardless of how you arranged it. Okay? So what's neat about it, does that mean that I can't pick poison pivots? No. If I'm very unlucky, I'll pick the worst one of the examples, right? And next time I pick a random number from 1 to n minus 1, if I get very unlucky, I'm going to pick the one that has the worst possible pivot. And if I do it again, I'm going to get, maybe I pick another random example. So there's a chance I could be unlucky n straight times, right? But it's very, very hard to be that unlucky. Does everybody kind of get that idea? Usually, if I'm really picking things at random, half the time it's going to be a good pivot, okay? And everything is going to work out just fine. So what's the really neat thing about is that if I pick a random pivot, I get to say the following. With high probability, no matter what you give me as input, my quicksort is going to run in n log n time. If I don't use randomization and I just use a fixed pivot, well, I can say, well, if you give me random input data that's been mixed up, or you don't put the pivot in bad places, quicksort is going to usually run in n log n time, right? Does everybody see that this is a much stronger guarantee? There is no bad case to mess me up on. There's only questions of luck, and luck is on your side, okay? You know, if, it could be, if let's say I agreed I was going to shoot someone in this room, if I flipped coin heads 100 times, and it came up heads every time, okay, you guys shouldn't get nervous, because the odds of that is so low that, that it isn't going to happen. And that's the idea of basically randomized algorithms. Any questions? If I did flip coins and it started coming up heads 50 times in a row, then you would probably get nervous about the quality of the coin, right? Okay? But you would recognize that the probability of that is vanishingly small. Any questions? Okay? So randomization is kind of an important idea. And, you know, we saw it sort of in hashing. Hashing is kind of randomized in the sense that people say, in constructing their hash function, essentially, if you pick the coefficients of that hash function, kind of, sort of at random, nobody can design a set of keys that you're going to always hash to the same bucket. Right? What were we always afraid of with a hash function? You could imagine if Donald Trump, or not forget the Donald Trump thing, but if I wanted to make your hash table look bad, if you give me the hash function with the coefficients that you're using, I could design keys that will all hash to the same bucket. Does everybody agree with that? But if instead you make me give you the keys, and then I randomly pick the hash function, the coefficients of my hash function at that point, there's no way I can design elements that you're going to that you can purposely mess me up on. Does everybody see that? And so, bottom line is this idea of randomization is very good for avoiding worst cases, for making things, easier to analyze, like our nuts and bolts example, okay? Because we picked a random nut and bolt, okay, randomization gave us a good algorithm for that, whereas I couldn't come up with an n log n worst case algorithm for that. Yes? Is a randomized hash quicksort. So you're saying is randomized better than getting the median? Okay, see, notice that n over 2, picking the median out. So if I have if I have an array here, and I'm saying I'm not going to fall for this trick of picking the last one, I'm going to pick the item that's in the n over 2nd position as my pivot. If I do that, what would the evil adversary do? They would put the biggest item, in the n over 2nd spot. No, what is clear is if I know your quicksort program, and there's no randomization on it, I can cleverly put together a permutation that your program will do badly on. If Donald Trump was trying to make Hillary's program look bad, and he had the best people on it, and he had a copy of that program, and it was not deterministic, there is a worst case for it. And you could design it, and if I give you that, you're helpless. But if you pick the pivot at random, no matter how much you scheme to design a bad case, there is no bad case. They all look the same to the algorithm. Yes?
When you randomize something, don't you have to make an algorithm to generate the random numbers?
So you need an algorithm to randomize, use randomization, you need an algorithm to generate random numbers. And there are, how many people here have ever used a random number generator? Okay, so most people, where you have a program, a function in most libraries, programming language libraries, that will generate random numbers. What it means to be a random number is a little bit of a dicey question, okay? And, but basically, for our purposes, there are these various algorithms that generate streams of numbers that look like random numbers. Look random enough to us to be good for these kinds of things, okay? Whether something is random in a quantum theory notion or random in a... But there are these pseudo-random generators that do a good job generating numbers that look enough like random that make these kind of algorithms attractive. Yes?
These are all O1, right?
And it takes constant time to generate a random number, okay? And these things are fast, okay? Any questions? So randomized, we're not going to talk about them a wild amount in here, but recognize that they are good things, and they are important things, and, you know, they're a good way to avoid problems, okay? Any questions? And I distinguish, the one thing that I guess I want to be clear by the end of the day is that I distinguish randomized algorithms from kind of feel-good heuristics. Randomized algorithms have random numbers making decisions, not saying, oh, the data usually does the right thing. There's a little bit different, because what the data is going to look like depends upon what the worst case is of the algorithm. In a randomized algorithm, there is no worst case input. There is only lucky or unlucky. Whereas in a deterministic algorithm, there is always an example that is hard for your algorithm. Okay? Any questions? Okay. Okay, so is quicksort faster than heap sort? People have been asking me this a bunch this week. What do I say? The answer that I would say is that I think about algorithms in the big O dominance level. If you ask me, is heap sort faster than selection sort? I will say yes. In the worst case, one is quadratic, one is n log n. Okay, it is clear that one is better than the other, end of story. If you ask me to compare two n log n algorithms at the level that I would talk to you guys in here, I will say I don't really know. I don't care. There's constants that I'm hiding in the big O, right? Maybe one guy's constant is bigger than the other guy's constant. And unless I do a much deeper level of analysis, I couldn't hope to tell. Okay? And usually it doesn't pay to try to do that kind of deeper analysis. What I can tell you is my people who've implemented this tell me that in practice, typically a good quicksort will run 2 to 3 times faster than a good heap sort. Are they right? Who knows? As a big theta thing, big O thing, they're both n log n expected time. Okay? In practice, one seems to do a little bit better. Okay? But that's not the level that I would really want to be able to do the analysis here. Okay? Any questions about it? So I'm perfectly happy at the big O level of reasoning here. Any questions? At some point you do experiment. I say big O theory-wise to tell differences. If they're tied big O-wise, then you do experiments. Any question? There's no reason to do an experiment about whether heap sort is faster than selection sort. That's a done deal. Okay? Any questions? Okay, good. Okay, what I'd like to now go through for a little while is actually to an interesting theoretical question, which is whether there is a better algorithm than n log n for sorting. We've shown you a zillion n log n sorting algorithms, right? Nothing special about an n log n sorting algorithm. Is there any chance we might be able to come up with a faster algorithm for sorting? Okay? In the worst case. Okay? And I'm going to argue that there isn't. okay? And I'm going to give you a sort of a proof idea, a proof that there isn't a faster algorithm for comparison-based sorting than n log n, okay? And this is kind of an interesting, what do I mean by comparison-based sorting? All the algorithms we've talked about sort by comparing two items to each other, right? What did quicksort say? Are you bigger than the pivot or less than the pivot? What did insertion sort say? Are you bigger than the guy that's before you or not, right? So all of the thing that's driving it is how many pairs of elements are we testing to see which one is bigger than. I'm now going to give you an argument as to why there cannot be a faster algorithm than n log n in the worst case for these kinds of algorithms. And it's going to be based on the following idea, kind of. That if you think about if I give you a sorting program, okay, if it's a deterministic sorting program, if I give you the same input again, it's going to do exactly the same thing, right? It executes a certain number of steps inside, compares the first element to the second element. If that came up bigger, then it compared the first element to the 96th element. It works in a particular flow, okay? What I claim is that we could describe any sorting algorithm. If I give you a sorting algorithm, we could write it as a tree of comparisons. Okay? What sorting algorithm is this? Look at this. What sorting algorithm is this? Can anybody tell? Okay. Does it look like a sorting algorithm? Does it look like quicksort? Does it look like insertion sort? Does it look like selection sort? Okay. Doesn't look like any of these, I guess, right? Why do I say this is a sorting algorithm? I think this is insertion sort. What is this algorithm doing? Well, it is showing a tree of comparisons. It is saying, suppose I have a input of 3 items. My input is going to be a permutation. Let's say the item's 2, 1, 3. Let's say I'm going to insertion sort 2, 1, 3. What am I going to do? My first step is going to be to compare, is this one bigger than that one? Does everybody agree? If it is bigger, it is bigger than that, right? Or one is less than that? Implicitly, I then kind of arrange this. Does everybody see that? And now I have to compare, is this guy bigger than what was the first guy? If it was smaller than the first guy, then the arrangement is right. Does everybody see that? Okay. My claim here is that you see here a tree which has all permutations of 3 elements. How many permutations of 3 elements are there? 6. Okay. In sorting 3 elements, the sorting program has to do something different in every one of these permutations. If it did exactly the same thing, it would leave them in the same that would mean that one of them wasn't sorted properly. Okay? So let's look at what the first one's saying. Compare the first element to the second element. If the first element of the input is less than the second element of the input, then what would selection sort do? If I had 1, 2, and 3, it would compare this. It would insertion sort. It would leave it like this. If this was bigger than that, now the first 2 elements are sorted. Does everybody agree? If I now compare the last second element to the first to the third element, if this is bigger than that, that meant that the elements are sorted. Does everybody see that? Let me say this one more time. Does everybody see that in insertion sort, if the items were 1, 2, 3, what it's doing is comparing the first element of the input against the second element of the input. It decides that this is less than that, so this is fine, right? It then compares the second element of the input to the third element of the input to the second element of the input. If it finds that this is bigger than that, then insertion sort would say that it's done. Does everybody agree? So that's exactly what happened here. Does everybody see that that the path down to the leaf is the step of comparisons that happen to sort that permutation? Okay? The first comparison was if A1 is less than A2, we go to the next branch, and then if A2 is less than A3, then we're done with insertion sort. Okay? Because that meant the element was sorted. Okay? How many people believe that this describes insertion sort? Okay, you have to verify it for the other paths. But I claim that if you take for any permutation this tree and you go from the root on down, this will describe what insertion sort does. Okay? Now, how much time, what is the worst case running time? If this is insertion sort, what is the worst case running time of insertion sort? It's the height of this tree. Does everybody see that? That's the time it took on the hardest element. The height of the tree, of this tree, is exactly the worst case time of it. Right? So let's say, what do I want to claim here? Okay? That if I want to argue that no tree, that no sorting algorithm can do better than n log n, what I really want to say is it's impossible to build a tree that has as many leaves as sorting requires, okay, whose height is less than n log n. Does everybody kind of get that idea? How many leaves are there? If I have n items, how many possible things is sorting going to have to be able to work on? N factorial different things, right? So what I really want to know, the thing that's going to drive this is, if I'm claiming that any comparison space sorting algorithm is described by a tree, its worst case is going to be the height, okay? If I'm going to have n factorial leaves, what is the shortest possible tree I can have that will have n factorial leaves? Log of what? Log of n factorial. Does everybody see that? So the height of this tree is going to have to be greater than or equal to the log of n factorial. Okay? What is the log of n factorial? Well, you're saying n log n with the confidence of knowing the answer at the end. Okay? But why is it n log n? Okay? Yeah? Okay, so you're saying if you know Stirling's approximation, okay, you're saying you know Stirling's approximation. There is a famous approximation that n factorial is approximately n to the n over e, n over e to the n. What is the log of n to the n? Does anyone remember what the log of n to the n would be? It's n times the log of this thing, which is n log n. Does everybody see that? Okay? That if n factorial is in fact really close to n over e to the n, this should convince you. And many of you say, well, Stirling never told me his approximation. But let me show you how I would reason about it, okay? Which is instead to say, it is clear to me that n log n factorial, has to lie comfortably between, it's got to be less than n to the n, and it's got to be greater than n over 2 to the n over 2. Why is this? N factorial is the product of 1, 2, 3, up to n, right? Is that going to be less than the product of n, n, n? Yes, that's what's here. Second, is it clear that n over 2 to the n over 2 is less than n factorial? The answer is yes, because if I take the numbers 1 through n here versus n over 2, n over 2, n over 2, the product of these n over 2 numbers in n factorial are all bigger than n over 2. Does everybody see that? And so it's clear it's between this. What was the log of n to the n? You told me that was n log n, right? What's the log of n over 2 to the n over 2? That was going to be precise, n over 2 times the log of n over 2. What is the log of n over 2? This is something like log n minus the log of 2. What is the log of 2? Constant, right? N over 2, this is n times a constant, right? Thus we have proven that the log of n factorial is theta of n log n. And so my claim here is that any sorting algorithm that's based on comparisons is going to require n log n time. Yes? What kind of sorting algorithms aren't comparisons? Okay? Let's propose a couple of, what? Let's say you would call counting sort. Let me propose an idea of one. How are we going to sort your exams? Think about it. On Tuesday, you guys are turning in 215 exams. Somehow we got to sort these at the end. How is the TA going to sort them? Are they to compare every pair of exams and say, oh, this one's before that one in alphabetical order? How would you sort these paper exams? You would probably say, give me a big piece of floor, put the A bucket, B bucket, C bucket, D bucket, all the way through letters of the alphabet, and toss them based on their first letter into a bucket. Does everybody see that? And now I've got smaller numbers of people whose last names begin with A. Now maybe I could toss those into some secondary buckets, or if it's small enough, just sort them. Does everybody see that? Now I'm not comparing elements against elements. I'm comparing the first letter of your name against a letter written on the floor, right? Does everybody see how that's a little bit different in flavor? Okay? So in particular, let me propose the following kind of an algorithm for sorting. Suppose I had n numbers to sort, which were uniformly drawn from 1 to n. Okay? Then what I could do is set up n buckets, each of which is of size m over n, so they're equal units of space. Okay? If the numbers are uniformly drawn from 1 to m, okay, and I have n buckets, on average, each bucket will end up with one of the n tests, right? If I now, to decide what bucket a number is in, I'm just going to be taking the remainder of that number mod m, okay? To figure out what bucket it goes into is basically just a division. Take the number x and divide it by the width of a bucket. That's going to tell me which bucket it goes into. So with constant time, I can take any number and decide which bucket it's in. Do people see that that's true? If the bucket has a width, dividing the number by the width tells me which bucket it's going to be in. Okay? In constant time, I can decide what bucket it's in. I toss it in the bucket. If the numbers are uniformly distributed, I should have on average, one item per bucket. Not going to get too many items in any one bucket. Okay? And now I can go along and basically sort these constant number. How much time does it take to sort a constant number of things? A constant, right? So I can just walk through and say, these guys are first, sort them. Next, nothing. Sort these two, next. Okay? How much time should this be? To toss the items into the bucket took order n. To read them out took order n. Okay, to sort them within each bucket took, at most order n. This should take order n time. Does everybody see that? What happened to my lower bound? Okay. Why does this not bother me with respect to my lower bound? Okay, looks like an order n sorting algorithm, but why does this not replace my worst case bound? Yes? It's a non-comparison sort, but if I told you that I'd proven a lower bound for sorts that stood on one leg and danced, okay, that wouldn't mean I couldn't do something deeper. Why in particular does this not violate the spirit of my lower bound? Yeah? It works under the specific assumption that my numbers were uniformly distributed between 1 and m. Does everybody see that? If I have to rely on my sorted elements being distributed, if I was, what do you think was going to happen when the TAs look at these letters? They have the 26 buckets for all the letters. How busy do you think the Q bucket's going to be? Not a lot of Q's, right? They're going to probably be a lot more in the S's, right? So distributions, if you're assuming something about the input, you have the chance to get screwed. Does everybody see that? You could end up with the case where, out of all these numbers, if I say here are n numbers less than m, sort them, I'll put them into these buckets. There's no law that says that they couldn't all be small numbers. Maybe the numbers were drawn from midterm grades in here or something like that. Okay. Any questions about that? Does everybody get the point? That bucket counting thing, implicitly, to make that run in n log n time, it assumed that a property of the inputs being drawn nicely. Does everybody get that? Okay. And you can't always assume that you know anything about your data distribution. This is why we worry about worst case distributions. A lot of the times when you assume things about data distributions, you will find your assumptions are wrong. For example, if we looked in a telephone book, okay, like the Manhattan telephone book, how many Skienas are there going to be in the Manhattan telephone book? A lot of Skienas or a few Skienas? Very few. It's me and Cousin Alan, okay? How many Smiths are there going to be in the Manhattan telephone book? A lot of Smiths or a few Smiths? A lot of Smiths. How many Shiflets are there going to be in the Manhattan telephone book? Okay, has anybody ever met someone named Shiflet? Okay. Now, let's take a look at a smaller place than Manhattan, Charlottesville, Virginia, where I went as an undergrad. How many Shiflets were there in the phone book? Here is a picture from the Charlottesville, Virginia phone book. Charlottesville was a small town of 50,000 people. And if you look at their telephone book, they had a James C. Shiflet, a James E. Shiflet, another James E. Shiflet Jr., James F., James J., James K., L, O, O, R. Okay? There were a shifload of Shiflets there, right? Now, why is that? Okay? Okay? If you know about the distribution of names, this shouldn't happen. Okay? But why does it happen? Turned out there was a mountain clan that historically lived in the area, and there's all kinds of legends about this clan down there. But basically, there were 3 pages of Shiflets in the very thin Charlottesville phone book. So what's the principle here? We don't like algorithms where we make assumptions about what the distribution is, because then we would get messed up. What would happen if we tried to do a bucket kind of a sort on the Shiflets? We would toss them into the S bucket and then say, oh no, they're all there. I know, let's hash them on the second level. Suddenly the H bucket, everybody goes into the H bucket. We look at it again, let's look at the I bucket. Everybody's there. Does everybody see that in all these layers, you can do all this bucketing and make no progress? Okay? So the principle here is this is why we worry about worst-case algorithms. First of all, trusting the input distribution is terrible. This is not about a randomized thing. This is saying if you're assuming something about the input, you're making a mistake. Okay? If you're going to randomize these things somehow, and toss them in random bucket, well, now randomization, it's about luck and not about the input. And that's okay. But of course, the best thing is one that will always give you worst case good bounds. Any questions?
What if all the people kick the bucket? Would that be okay?
Okay, no comments about that. Okay, any questions here? Okay, any other questions? I think we've got 2 minutes left. Any other questions about the exam or anything like that? Okay, yes?
In a case like this, what would you hash
Okay, so what's important here is tossing names into a bucket for sorting purposes. I couldn't use an arbitrary hash function. Do you see that I needed my items, my buckets, to be sorted at the end? So my hash function is in some sense fixed at that point. There isn't a good hash function to sort by. There's a good hash function to group similarities by. But for sorting, hashing is not a good thing, okay? Because you don't have control of that. Okay, thanks very much. If you have any questions, talk to me afterwards.